I'm Michaela Souza, and this is a presentation of the study Numerical Evaluation of Tubular Performance Shear Connectors. This study will be presented divided into an introduction, a numerical model development, an evaluation of tubular performance connector, and conclusions. Steel and concrete composite systems are the efficient and economic structural solution. This composite system has been widely used in civil construction. The interaction between these different materials is essential. Shear connectors are the most common means of ensuring these interactions. They are the key elements of the composite structures when they make the composite behavior happen, minimize the slip between the materials. These connectors, which must resist the relative slip and uplift between the concrete and the steel, can have different geometric shapes. Many shear connectors have been developed in the last decades, such as stutter bolts, C-profiles, U-profiles, cross-bond, perforbond, and C-perforbonds. The performance connector was conceived and has stood out. It is known to have a greater behavior, however, sometimes doesn't present adequate slip capacity. There is a need for an alternative connector to the performance that can achieve adequate slip capacity, as recommended by Eurocode 4. Thus, from this need, a tubular shear connector is proposed. It is expected that a tubular cross-section can optimize the connector performance, and the proposal is that the concrete confined inside the connector provides a greater slip capacity when compared to the regular performance connector. As no results of a connector similar to the one proposed here were found in the literature, a validation of the numerical model will be carried out from the results of the performance connector of Vienna in order to validate the model choice. Among all the models studied by Vienna, the performance connector with two holes was chosen for the numerical validation. Development of the numerical model. The study was performed in Abacus 6.14 and the explicit software was used in the nonlinear numerical analysis conduct. About the geometry, the experiments performed by Viana was based on Eurocode 4 and all components were modeled with solid elements. The load was applied by displacement on the high-profile sexual surface, and the boundary conditions were defined as restriction to the displacement in the two directions of the global X. About constraints and interactions. The embedded constraint was applied to simulate the interaction between the reinforcement bars and the concrete. The tie constraint was applied to simulate the weld between the shear connector and the steel beam. The non-hard contact and the tangential contact behavior was applied to avoid the overlapping between the pairs during the simulation. About the mesh, all the components of the model were discretized with 3D elements of type C3 GHR with an overall size of 5 mm for shear connector, 24 mm for reinforcement bars, and 8 mm for slab and steel beam. The elastic perfectly plastic stress strain model was applied for the beam and the rebar. The quadlinear stress strain model was applied for the shear connector. The concrete was modeled from the concrete damage plasticity model. The concrete strength employed were 28 and 52 megapascal. The constitutive model proposed by Pavlovich was adopted to characterize the behavior of concrete under compression, and the bilinear tensile model recommended by Model Code was adopted to characterize the behavior of concrete under tension. Analyzing the validation results, two models of the perforbond connector with two holes were analyzed with 28 and 52 megapascal. About the models, NEM is used to indicate that they are numerical models and EX that they are experimental models. The numerical model with 28 megapascal presented an ultimate load 4% higher than its experimental models. The 52 model obtained a 10% higher ultimate load when compared to the experimental one. So there is a satisfactory agreement for the model with 28 megapascal. The 28 megapascal numerical model presented the initial stiffness similar to the experimental one. After reaching its peak load, the numerical model lost stiffness faster, which justifies the lower slip capacity. The 52 megapascal numerical model lost stiffness lower in the post-peak segment, resembling the experimental one. The 28 model was validated in terms of peak load and the 52 in terms of post-peak behavior, but it is important to mention that other studies are needed to improve the validation. Evaluation of tubular performance connector. The numerical model shown before was applied in the tubular connector study, including materials, constraint, context, boundary conditions, mesh, among others. The tubular connector has been studied as without holes, with 2 holes, and with 2 holes and rebar. To minimize computational costs, only a quarter model was modeled using double symmetry restriction. 2 concrete strengths were studied, 28 and 52 megapascal. The influence of the hole and the rebar were also evaluation. About the models, the TP index indicates tubular performance. The N8 denotes that connector has no hole, 28 denotes that it has 2 holes, and PR denotes that it has a rebar. 28 and 52 megapascal indicate concrete strength. About the results, all results were taken according to Eurocode 4. About ductility, Eurocode 4 defines that the shear connector is ductile if its characteristic slip capacity is at least 6 mm. Thus, only the first connector without holes were not ductile. The use of the holes and the rebar led to increasing the shear strength of the connectors. With the exception of the no-hole with 28 megapascal, all models exhibit ductile behavior after the ultimate load. The use of the hole and the rebar conferred a discrete increase in the resistance. For all models, it led to connector peak load equal to higher values. The increase of the concrete strength resulted in an improvement of the shear connector strength for the different case study, ranging from 15 to 18%. There was an expressive increase in the slip capacity of the tubular shear connector due to the rise in the concrete strength. The variation in the strength of the concrete didn't influence the steel yielding, only the concrete crush pattern. Tubular performance connector versus performance connector. About slip capacity, the proposed connector presented 182% more than performance for model with 28 megapascal and 98% for the model with 52 megapascal. The tubular performance connector presented shear strength 4% to 90% lower when compared to the performance one. However, the area of the tubular connector is 18% smaller than the area of the performance connector. Thus, the proposed tubular performance connector has such a strange potential as the performance connector. About the conclusions, the model validation indicated that the numerical choice led to an adequate calibration in terms of ultimate load. However, it is still necessary to study the post-peak behavior to increase the connect ductility, as observed in the experimental program. About the tubular performance connector, the presence of the holes in the rebar contributes to their post-peak ductility. for the models with concrete strength 28 megapascal. The presence of the holes modified the connector yielding. The increase of the concrete strength influenced the connector behavior, leading an increment of 15 to 18% of its resistance and 83 to 289% of its slip capacity. Except for one no-holes connector, all the proposed connectors could be considered ductile by Eurocode 4. It is important to study new parameters and conditions, but this tubular connector proposal can be considered feasible. Compare the tubular performance connector with performance connector. The tubular performance connector reached the desired ductility, presents excellent post-peak slip capacity. The use of the tubular performance connector discreetly decreases the concrete crust propagation for models with both concrete strength. We would like to thank the project funders, CAPES, CNPq, FAPERJ, and the research group Architecture for the financial support to this program, and to thank you all.